For our final example for the section, and actually for all of chapter 4, we have one example left, and we're going to look at the Sierpinski triangle. It's a sequence of triangles, and we are going to find the areas of each stage and the perimeters of each stage. I'll describe that, what we mean, in just a second. So first, let's figure out what stage 0 is. Draw an equilateral triangle and shade it. Okay, so here's our first one. And before I shade it, I'm going to go, let's see, call the area A. So I'll just say area, capital A. And now I'll shade the entire triangle. That's stage 0, area A. Okay, so that's the stage 0 triangle. Now, what are we going to do for the stage 1 triangle? Start with the stage 0 triangle. Mark the midpoints of the 3 sides. I did it as close as I could here. The midpoints of each of the 3 sides. This is going to be stage 1. Remove the equilateral triangle that has those vertices. So make a triangle here, like so, and remove it from the triangle. So that means now we don't include that one we just created. It's just the remaining portion. So that's the area for stage 1. All right, now let's do stage 2. Stage 2 is going to be take the stage 1 triangle and remove the middle from each of the shaded triangles, just like we did before with the larger triangles. So we're starting with stage 1, and now we're going to do this. Go to the midpoints and remove that triangle. See how we're doing it with each shaded triangle over here? Remove this middle one, remove this one. Make sure you shade the right small triangles. And then on this triangle, we'll remove the middle triangle. Shade like so. Okay, well, we've shaded stage 0, stage 1, and stage 2. And stage 3 would look like stage 2, but we would remove the middle out of all of these. How many triangles? 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles. That's enough, though. So now let's compute the areas at each stage, and then we'll compute the perimeters at each stage, and we'll be done. So what I mean by the area, that's obvious. It's the shaded region in each stage. The perimeter, obviously, the perimeter is going to be these 3 sides. Over here, though, the perimeter is that, and then all of these as well. So it's the perimeter of every shaded region. So the perimeter here is the 3 sides of all of these shaded triangles. Let's start with area. Doesn't matter what we start with, area is some positive number here. So I'll write it again, area A. Well, what's the area of this triangle? Should be easy to see. Notice that we broke this triangle up into 4 regions of exactly the same size. 1, 2, 3, and 4. Yet we removed one of them. Okay, so how many of these fourths, 1, 2, 3, 4, are there left? 3 of them. So we basically removed exactly 1/4 of the area. So this will have area 3/4. All right. Oh, sorry, 3/4 A. What am I talking about? 3/4 times A. Well, what are we removing here from the shaded areas? We're removing 1/4 of every one of these 3 shaded triangles. We're removing that, that, and that. So the remaining area is going to be 3/4 of the previous stage area. That's going to be 3/4 of this. In other words, 3/4 squared times A. So what happens to the area as the stages go on? Area goes A, 3/4 of A, 3/4 squared of A. The next stage, stage 3, would be 3/4 to the third times A. Well, that's enough. What does this go to? This sequence of numbers, it does not matter what number A is. If you take 3/4 of it, and then you take 3/4 of that, and then you take 3/4 again, it's absolutely going to approach what area? 0. Any number that you choose and you multiply by 3/4 times 3/4 times 3/4 forever, that is going to approach the number 0. So the limiting area is 0. Now let's take a look at the perimeters. Let's just say that stage 0 has perimeter P. I was considering saying 3S, where S was the length of the side, but let's just say the whole perimeter around the edges is just perimeter P. Perimeter P. Now, I want you to tell me what's the perimeter here, what's the perimeter here, and in general, how does it proceed? What would the perimeter of stage 3 be, and so on. Okay, well, all we've done is the perimeter here is going to be the same perimeter as before, right here, and then we have to add these segments here to the lengths of these. So one way to think about it is I'm going to take this area, thinking of it as P, and this is going to be a bigger number, right? Because we're adding to it. We're adding some additional segments. How long are those segments? They're exactly 1/2 of length of one of the sides, correct? Because we're adding this, that. This is an equilateral triangle. These are all equilateral triangles. So instead of having 1, 2, 3, 4, 5, 6 of those half sides, I'm just putting a mark in there to indicate that they're all the same length. We now have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we basically went from 6 to 9. So how did we increase? The ratio is we went, what used to be 6 is now 9. Well, what is 9/6? That's the same as 3/2. So we increased by 50%. We used to have 1, 2, 3, 4, 5, 6 of these half lengths, and then we jumped it up to another half of 6, which is 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the perimeter of stage 1 is 3/2 times P. Well, that was the hard work. Now notice every single one of these little shaded triangles here went from, if you think of 1, 2, 3, 4, 5, 6, it went to 1, 2, 3, 4, 5, 6, 7, 8, 9. We did exactly the same thing. The perimeter just jumped by a factor of, well, 3/2 times the previous one. So 3/2 times this is going to be 3/2 squared times P. And then, so this would be stage 0, 1, 2. Stage 3 would be 3/2 cubed times p. And it goes on forever. And what does that converge to, or does it converge? P is a positive number, the perimeter is. And then we're multiplying it by 1.5. And then we're taking that and we're multiplying it by 1.5 again. That's an increasing sequence. The numbers just get bigger and bigger and bigger and bigger. So the perimeter actually approaches infinity, which is very interesting, the Sierpinski triangle. The area goes to 0, yet the perimeter, the lengths of all the diameters of all of these shaded triangles approaches infinity. Now I printed out a picture of the Sierpinski triangle after maybe, well, let's see. This is after about, I'm guessing 8 or 9 stages. As you notice, we removed this triangle, and then we removed this triangle, and then we removed this one, this one, this one, this one, this one. I don't know how small that gets. Let's say it's stage 10, something like that. So the higher the stage goes, the more white it's going to become. The area, the shaded region, is going away. So there we go. Very famous problem, the Sierpinski triangle.